All right, so our next three sample problems are going to use something that we kind of learned in the beginning concept of this chapter. First law of thermodynamics says that energy cannot be created or destroyed, it's simply converted into alternative forms. That is, some type of process that takes in or gives off heat is going to give it to or take it from another system. And we're going to call those two systems the surroundings and our system. And so what we're going to see in the next few sample problems is we're going to have physical changes that we're going to see in terms of heat exchange. We're going to see chemical process that we see in terms of heat exchange, and we'll see chemical process in terms of combustion that we'll see with heat exchange. So our first problem that we're going to have here has to do with heat exchange between a hot piece of metal that we put into room temperature water. So again, you know me, I love to draw pictures, so I want to draw some pictures for this so that we can see what's happening. So we've got 22.0 grams of solid in a test tube. We heat it to 100.00 degrees Celsius. Then we add it to 50 grams of water in a coffee cup calorimeter. The water changes from its starting temperature of 25.1 and it heats up to 28.49. So we'd like to find the specific heat capacity of the solid. All right, so anytime you see problems like this where you're having heat being exchanged between two systems, we need to treat the problem as kind of two independent heat capacity problems that we're going to couple together. So let's draw some pictures here so if we can see if we can make sense out of this. All right. So I'm going to have my little beaker of water. We've got 50 grams of water. We've got it at 25.1 degrees C. Let's imagine I just dropped a little cube of metal in there, and it's 22.05 grams of this solid metal at 100 degrees C. I know I asked this in class. How could we make sure to heat something up to exactly 100 degrees C? 100.00 degrees C. You must have had it in boiling water, right? It's a great way to heat something to a precise temperature. All right, so I just plunked this hot metal into my room temperature liquid. And again, we're going to sit here and we're going to wait. And we have this in an insulated coffee cup calorimeter, so we're not going to lose any of the heat to the surroundings. So we're going to wait until we see an equilibration or a stabilization of the temperature of the water. And at some point, again, our cube's still going to be in here. Our cube didn't lose any mass. It's 22.05 grams. We still have 50 grams of water. And our 50 grams of water, again, is going to have heated up. The mass of our water will have cooled down. And when something heats up, that means it takes in heat. So a positive Q for our water. And cooled down means it gave off heat. So a minus Q for our solid here. And at the end of the day here, the temperature of both of these, so the temperature final of both is going to be equal to 28.49 degrees C. So conceptually, and we kind of introduced this at the very beginning when we talked about thermodynamics, the concept is the energy of the system and the energy of the surroundings compensate such that there's no change in the energy of the universe. So any change in the system must be accompanied by an equal and opposite change in the energy of the surroundings. So what we can do is we can set these two Q values equal to one another. The heat that's given off by the solid must equal the heat that's taken in by our water. So again, Q solid is the heat given off by our nice little cube of hot metal, and Q water is the heat that's given to my little beaker that has water there. Okay? So remembering that each Q is equal to Q times M times delta T, we can create two equations that we set equal to one another. Keeping in mind this Q is negative, I'm going to have a minus heat capacity of the solid times the mass of the solid times the change in temperature of the solid. That's going to be equal to, and again, this is heat gain, so I'm going to have a positive heat capacity of water times the mass of water times delta T of water. Okay, so let's see if conceptually we know all these pieces of information. Mass of the solid, check, we know that. That's 50 grams. Oops, I'm sorry, that's the 22.05 grams. Mass of solid, 22.05 grams. Mass of water, 50 grams. Okay, specific heat capacity of water, we know that as 4.184 joules per gram Kelvin. Heat capacity of the solid, oh, you know what? They tell us to find the specific heat capacity, right? So that's okay that we don't know that. That's our one variable. That's our unknown. Temperature change in the solid. Remember, delta T is always T final minus T initial. We know that the T final is 28.49 degrees C. The initial temperature was our 100. Delta T for water, we know that the final temperature is 28.49, and we're going to subtract the initial temperature, which was 25.1. And again, degree C, degree K, I shouldn't say degree K, degree C or Kelvin are going to be the same increment, so we can put our Celsius in there. So we have all the pieces of information that we need. I'm going to go ahead and take this equation and I'm going to rearrange for C solid. So see if algebraically this makes sense. C solid equals, I'm going to move my minus over. This stuff is all going to be in the numerator. CH2O times mass H2O times delta T H2O. And then we've got our mass of solid and then our delta T of solid. Okay, I'm going to put in the mathematical solutions to this. We've got minus 4.184 joules per gram Kelvin, 50 grams, and then 3.93 Kelvin. Okay, that's positive because our water heated up. Denominator, 22.05 grams for the mass of the solid and a negative 71.51 Kelvin. Again, we know that our block cooled off, so the delta T is negative. Go ahead and solve for your C solid, and you get 0.450 joules per gram Kelvin. Notice that grams are going to cancel there, Kelvin will cancel there, and we're left with units of joules per gram Kelvin. Notice the minus signs will cancel here. So we're left with a positive value, as you should for a heat capacity. Go ahead and if you were to look this up on table 6.2, you could actually identify what metal that is. It's likely that this metal was iron.